Question 2. This question is about capacitors charging and discharging. So we've got a standard charging circuit, but we've put in a variable resistor here, and if you read the words, then their intention is to maintain a constant current. So it's different to a normal capacitor charging experiment. Normally you would use, the current would change as the capacitor charged up, but we're adjusting the current to make it constant. So students should use a digital voltmeter for the experiment. Digital voltmeter has a very high resistance. Why is very high resistance for a voltmeter important? Okay, so this is just a general question. It doesn't have anything to do with this particular experiment. You want a very high resistance, so virtually no current flows through the voltmeter. So we've got I is equal to V over R, that's Ohm's law. So a high resistance means virtually no current flows through the voltmeter. Okay. 2.2, suggest one advantage of using an analog ammeter rather than a digital ammeter for this experiment. Okay, this question I can imagine could throw people. It threw me a little bit to start with. But I suppose if you've got an analog ammeter, so you've got like a needle like this, then what you could do is if you marked on a little point there, then you can adjust the dial here to try and make your needle point at that point there. That'll actually be easier to maintain constant current because you don't actually have to look at the numbers now. You just have to maintain the needle in a single position. How you explain that in words is going to be a little bit more tricky. So I'm going to try and write, you could draw a mark on the ammeter, or you could like stick some sticky tape or something on it, where the needle should point, which will make it easier to adjust for constant current. So you can't do that with a digital meter. You'd be constantly fiddling to try and get a number, which is a little bit trickier than that. It's a bizarre question, but never mind. Question 2.3, suggest a suitable full-scale deflection for the analog ammeter to be used in the experiment. Okay, so full-scale deflection is on the ammeter, whatever that value there is, the highest value that you've got there. Right, so this is basically using the information that you already know over here, try and make some judgments about what values you should be measuring in the experiment. So the first thing we need to think about is, do we want a big current or do we want a small current? Well, if we have a very large current flowing here, then what's going to happen is the capacitor is going to charge very quickly, and that's going to make the experiment harder to do. So we want a small current. So to make a small current, we need the variable resistor at its largest value. So we want a small current. So that will mean that the capacitor takes longer to charge. That will make it easier to do the experiment. So the maximum resistance will give us the smallest current that we can have. So when there's no voltage across there, because it's shorted out, all the voltage will be across there. So we have 6 volts and maximum resistance of 100k. So I is equal to V divided by R, which is equal to 6 divided by 100,000, which is equal to 60 microamps, I think. 6 divided by 100,000, press E and G, and it puts it as 60 microamps there. 60 microamps. Right, that's the current that we want flowing normally. So this doesn't ask for that though. It asks for the full scale deflection. Well, you can imagine these come in sort of standard values, so 50, 100, 200, 250, 500, that sort of thing. So we want 100 microamps, don't we? Because that would make that about halfway. So 100 microamps seems good. I think 200 microamps would probably be too much, but you can make an argument for other things as well. But I think that seems about reasonable. The diagram shows a reading on the voltmeter at one instant during the experiment. The manufacturer gives the uncertainty of the meter as 2%. Calculate the absolute uncertainty. This is a dead easy question. So it's 0.02 times by 2.39. So the absolute uncertainty, therefore, 2.39 times by 0.02 is that much. So delta V is equal to 0.0498. Right, now here's the trick, you've got to be careful. This mark is all about precision. So if you've got 2.39, you can have plus or minus 0.0, and then you've got to have your answer to this number of decimal places. So it's got to be that one. So that goes to 5. Plus or minus 0.05 volts there. This question just keeps on giving, doesn't it? Right, 2.5. Determine the number of different readings the student will be able to take before the capacitor becomes fully charged. Okay, so we've got some equations. The Q is equal to I times by T. That works for constant current, which this experiment is constant current. And we also have the capacitor equation, Q equals CV. So the amount of charge in a capacitor is CV. So the charge that flows due to the current is the same as the charge that will end up on top of the capacitor, because no current flows through the voltmeter because it's got an enormous resistance, or hardly any flows through. So IT equals CV. We want the time, so T is equal to CV over I. So that is equal to, okay, so C is written here, so that's 680 microfarads, that's times 10 to the minus 6. V, the potential across the capacitor, well, the maximum time that we're going to have is when this is fully charged, and that will be when it's up to the EMF of the battery, so that's 6.0 volts, divided by the charging current. Well, the charging current we worked out back here, so that's 60 times 10 to the minus 6 there. Which is equal to, well, my times 10 to the minus 6 is cancel. My 6 cancels with that 6, leaving 10, and that cancels with that, so that's 68 seconds. Okay, so we've got 68 seconds. Each reading takes 10 seconds according to this. So 10-second intervals means we can get 6 readings done, but not 7. So the answer they want is 6. But I would also argue that you get 1 reading at time 0, so I'm going to write that in, plus the initial T equals 0 reading. Now why am I writing it like that? Well, it's because I've looked at the mark scheme and it wants the answer 6. Now I think if you wrote 7 there, because you could have 0 and the 6 additional readings at 10, 20, 30, 40, 50 and 60 seconds, but you can't have one at 70 because there's not enough time, then in a real paper they would accept that because this would have been checked with real answers. So I think that would be okay. So don't panic about that if you decided it was 7. But it's a good idea to explain where your 7 comes from or where your 6 comes from, because then no matter what they say, the examiner will be able to give you the credit. So if the answer was 6 or 7, I would get the credit there because I've said 6 plus my initial reading, so I could get the 7, or 6 additional readings, I would get that credit there as well. So that's just a bit of an exam technique for you there. Right. Question 2.6. The experiment is performed with a capacitor of nominal value 680 microfarad and has a manufacturing tolerance of plus or minus 5%. The experiment, the charging current is maintained at 65 microamps. Data from the experiment has a straight line for the variation of PD with time. This shows that the PD across the capacitor increases the rate of 98 millivolts per second. Calculate the capacitance of the capacitor. Okay, so we're going back to this again, but we want volts per second. So we want V over T, and we're trying to get C equals something. So let's just go back to that bit there. So we have CV is equal to IT. We want V over T. So C times by V over T is equal to I. So therefore C is equal to I divided by V over T. And I'm going to leave it as V over T there rather than flipping it over and putting it on there, because that's what we're given. We're given volts per second there. So the capacitance is equal to 65 times 10 to the minus 6 divided by V over T, which is 98 milli, so times 10 to the minus 3. So let's put that into the calculator. 65 exponent minus 6 divided by 98 exponent minus 3 gives us, press the ENG button, 663.265 microfarads, and so we'll write that to 2 sig fig, so 660-2SF. Deduce whether the capacitor is in the manufacturer's tolerance. Well, 5% of that is more than the difference. Let's work it out, might as well. You can just see that it's more. So 680 times by 0.05 is 34. So it is intolerance because that is less than 34 away from that. So, is intolerance because 660 is within 34 of 680. There's probably better ways of wording that, but there you go. Question 2.8. Student decides to confirm the value of capacitance by first determining the time constant of the circuit when the capacitor discharges through a fixed resistor. Describe the experiment to do this. So this is one of the 12 experiments that you've got to just know off by heart, and you're going to be asked a question like this, so learn all the 12 experiments. So the circuit diagram, there are various things you can draw, but looks a little bit like this. We want a resistor to discharge it through. We also need to be able to charge it up in the first place. So let's put a power supply here. There we go. So that's what you should do. We're going to label some of these. Let's label the switch S, capacitor C, the resistor R, and this will label the EMF there. We need to be able to measure the potential difference across the capacitor. So we need to put a voltmeter. Oops. We need to put a voltmeter in there. Right, a voltmeter here would have done the exact same thing because these two are in parallel when it's discharging. Right, so what you do is you throw the switch to the left-hand side, that charges up the capacitor. Then when you throw the switch to the right-hand side, the capacitor starts to discharge through the resistor R. We also need a clock. There's my beautiful drawing of a timer. So put that down there so that you have a nice drawing of everything that you need. Right. Okay, we need to pick some values now. So we want to make this experiment take a reasonable length of time, but not hours and hours and hours. So I would suggest in the order of over a minute, but under, say, 5 minutes. So I'm going to say, let the time constant equal 100 seconds. Okay, so we think it's a 680 microfarad capacitor, so R will equal 100 divided by C, which is equal to 100 divided by 680 times 10 to the minus 6. So here goes, 100 divided by 680 exponent minus 6 gives us R is equal to 147k ohms. So that gives us a value to put R at, so 147k. And that gives us a reasonable value. So why did I pick 100 seconds? Well, 100 seconds is a reasonable amount of time to do the experiment over. 10 seconds is going to be too hard. 2 hours is going to be longer than you feasibly have at school, but you know, that's perfectly reasonable. So we need to describe the procedure first. Bullet points for a procedure is fine, so switch S to the left to charge the capacitor. Right, switch S to the right and start the timer. Record values of the voltage across the capacitor, so VC at various times for 100 seconds, or maybe 2 minutes. Let's put 2 minutes down. That's just the time constant, so if we put 2 minutes, take at least 10 readings. You don't even have to do the experiment, so you can say as many readings there as you like. And calculate LNV. Okay, I should show you why we're going to do that. So V is equal to V naught e to the minus t over RC. So if we take logs here, we got LNV is equal to ln of V naught plus the ln of this, which is the ln cancels out the e to the, so you've just got minus t over RC, like that. So if we do y equals mx plus c on this, y equals mx plus c, then we expect if we plot ln of v versus that, we should get the y-intercept being ln of our original voltage v, and we also should get the gradient being 1 divided by the time period, and it's negative. So plot and calculate ln of v, plot ln of v versus t. Now at this point I would always suggest sketching what you think the graph is going to look like. So ln of v versus t, and it should look something like this: a negative gradient, a positive y-intercept. Draw on your best fit line there, and calculate the gradient. Sorry about the noise of the rain, it seems to be getting worse. But calculate the gradient, and that will equal minus 1 over RC. Make sure you include that somewhere on your page, maybe up here. I've drawn it off the box here, which is a bit naughty. We don't actually need to verify what the capacitance is, because it just says to work out what the time constant is. But if you wanted the capacitance, C would equal to minus 1 divided by R times by the gradient. So just rearrange that to get capacitance. That's it, isn't it? We've calculated the gradient, and so RC is equal to minus 1 over the gradient, which is what it is that you want to calculate. And we also know that the y-intercept is equal to ln of V0. And my apologies for the noise of the rain. I will wait before I do question 3. Right, hopefully that's helpful.